So if you have, so now you have this notion of continuous maps, right? Continuous maps between one metric space and another, one topological space to another. When do we say that they're topologically equivalent? So the definition is if X, Y are two topological spaces, or say they are metric spaces. So these two are topologically equivalent if there exists a continuous map F from X to Y, okay, which is a bijection. Okay, so they have the same, so it's 1, 1 and onto. Okay, so set theoretic bijection, and the inverse map. Remember, if you have a 1, 1 map, then there's an inverse map, and it's since it's onto, then the domain of the inverse is the whole space Y. There's an inverse map that goes backwards from Y to X. Okay, so this is also continuous. Is also continuous. Another way of saying this is that, you know, there is a bijection that that is F is a bijection that takes open sets to open sets.
So,
yeah, tell me.
So why do we define the concept of continuity in terms of open sets?
Yeah. So we define it because it generalizes to very easily to other contexts, right? So what you need for a notion of continuity is that, you know, there are no sudden jumps, right? And so to make that precise, we have to have this concept of what a neighborhood is, right? So you don't go suddenly from a neighborhood of this point far away, right? So so you have to capture it by the notion of a neighborhood, and this is captured by the notion of an open set. Okay, so and then when you realize that, okay, for continuous you really just need the notion of an open set, then you can sort of define a space just in terms of open sets. You have an abstract space set X, and it has a collection of subsets which you call the open sets. Okay, and then you can define what a continuous map is in terms of those open sets. And this gives you a lot of flexibility. Okay, now you're not limited even to metric spaces. Okay, you can, so this notion, I mean, so there are various topologies that arise when people doing number theory. Okay, by the way, topology is used by across mathematics. Okay, it's not just geometry or topology people, you know, working with shapes. People working with numbers and number theory also, you know, have to deal with topology and notions of topology. It sort of pervades all of mathematics. And so for number theorists, sometimes the notion of what open sets are, for the number theorists, they're concerned with integers. Okay, so they're looking at 1, 2, 3, maybe the natural numbers. Okay, 1, 2, 3, 4 to infinity. And so you can define notion of open sets in that sort of a collection of things, okay, which might be different from you know, notion of metric. Maybe, you know, 2 and 3 are not close to each other, but 2 and 4 are close to each other, and things like that, right? So there are different notions of closeness that might be useful in different situations. So this notion of continuity makes that possible, okay? So yeah, so I mean, sometimes mathematics is not clear why something is useful. Why do we define it this way? But it turns out that they are useful because they offer more flexibility and that can be used in many other contexts and so on. And so as a student, one, you know, sometimes doesn't realize this, but as one goes on, one sees this, you know, sort of notion being used more and more, and then one realizes, it is useful. Okay, so yeah, so mathematics, you know, these definitions come up for a reason. They're not out of the blue. Okay, so they kind of you know, these notions of topology, these notions have been now sort of, they're, you know, they're more than 100 years old now, and they've kind of distilled over time to this collection of these notions, which are, so it's mathematics is a sort of a narrative. It's a story that starts off, sort of thousands of years ago, of course, but it's over time, concepts get crystallized and they get clarified and definitions get clarified. And then so ultimately what we are learning today is something as a result of a long, sort of thought process that has been going on for centuries. So there is a reason why, things are defined a certain way, which might not be immediately clear, but as one goes along, one appreciates them more and more. Okay, so in any case, so this is the definition of a topologically equivalent. It just says that you have these two spaces. They're the same up as a set. Okay, there's a bijection from one to another. Okay, there's a one-to-one onto map from one to the other. So this has a set of points. They are the same. But this bijection also takes open sets, what you call open sets on one, to open sets on the other. Okay, so the notion of neighborhoods is also the same. Okay, so once you have two sets which are identical as sets, and the sort of notion of neighborhoods are the same, then they're the same topological space. Okay, this is the notion of topologically equivalent, and this is called also called a homeomorphism. Okay, so F, this terminology. So let me say, note that F is called a homeomorphism between X and Y. Okay, so it's a homeomorphism, and then these two spaces are said to be homeomorphic. So X and Y are then, if this happens, if there is such a F, then X and Y are then homeomorphic. This is the notion of topological equivalence. Okay, there's another way of saying topological equivalence. So then homeomorphic, and it's and I'm going to denote it as so let me say it's sort of denoted as X. It's sort of equal to, with this tilde, Y. Okay, so I'm going to say that that's what it's homeomorphism means. Okay, so let me do a few examples just to sort of understand this better. So of homeomorphisms as well as non-homeomorphisms. Okay, so or a few more minutes. So let's look at this. So if you have an open interval which looks like 0, 1. Let's talk about an open interval 0, 1 in R. Okay, so so let's forget about R. Okay, so this is 0, 1. It's everything's in the real line at the moment. Okay, so it's 0, 1. So this 0, 1 is actually also homeomorphic to another open interval. Let's call it 2, 6. Okay, so this is homeomorphic to 6. Can someone suggest a continuous map which is a bijection whose inverse is also continuous, that maps the open interval 0, 1 to 2, 6? Can you define a map going from this interval to this, which is continuous and its inverse image is also continuous? Okay, let me tell you the answer. So if you take f of x is
something like 2x plus 2. It seems to be something like that.
Yeah, that's right. So if it's linear, let's say it's 4x plus 2, right? So then it will, at x equals 0, it goes to 2. X equals 1, it will go to 6, right? And so it takes this to that, and you can, this is obviously, it's a linear function, so it's definitely continuous. Its inverse is also, you can write down, right? So it's going to be a continuous. So the inverse is what? If you want to solve for 4x plus 2 is equal to y, right? So then the inverse, so x is basically y minus 2 by 4, right? Which is 1/4 y minus half. So that is also a linear function, right? So it's definitely also continuous, and it can show it maps 1 to 1. Okay, so a slightly more sort of tricky, perhaps, see that 0, 1 is actually homeomorphic to the entire real line. Okay, can someone suggest a way to do that?
Maybe, sir, 1 by x map.
Right, so 1 by x will not take negative values, unfortunately, but yeah, so the one can sort of try to modify it a little bit. So something like x by 1 minus x square actually works. And there are many maps you can come up with. So what you need is, so this 0, 1, you want a graph to sort of look something like this, right? So it wants to, the graph of f should sort of cover the whole of the real line, right? So that's what you need, and it needs to be sort of 1-to-1 and sort of continuous and so on, right? So you can check that this works. You can check that you can so this works. That's an exercise. You can actually explicitly find the inverse map, and this is obviously a continuous function, right? So you can, because it's made up of all these x and x square and division and addition, those are all continuous operations. And a similar thing happens, so let's go to one higher dimension. If you take an open disk of radius 1, okay, so this is in my notation from earlier, it's B10, so the open unit disk. Okay, so this is homeomorphic to R2. Okay, so again, so the plane. So just like in this 0, 1, this interval, you can kind of stretch to the whole of the real line. In this case, you have this open unit disk. You can think of it as a sort of taking an open interval and then spinning it around, right? So each, so you can sort of stretch each to a line, and then if you sort of rotate that line, you get the whole of R2. So you can actually write down a map if we can do for one interval in dimension 1, you can do it sort of in 2 dimensions and in even higher also. Okay, so so this is sort of maybe an exercise. How about so let me say, how about this closed interval 0, 1? Is it homeomorphic to R? Anyone? So now I'm sort of taking, sort of these 2 endpoints in the set as part of the set. Are these 2 homeomorphic? It's slightly more tricky. Okay, so Sharp says no. Can you say why? You can unmute yourself. Yeah, that's right. So somebody mentioned it's compact, right? So is that what you were trying to say, Sharp? Sure.
Yeah, that was what I was going to say. It would attain its maximum.
Yeah, that's right. So this is, here you kind of remember the property that if you had a continuous map from a closed interval 0, 1 to R, so this has a maximum value. It cannot go all the way, right? So you cannot have an onto map. Yeah, so somebody mentioned it's bounded. Okay, so this is not, it's not homeomorphic to R. So similarly, a closed square is not homeomorphic to R2, for example. So similarly, so if you look at a product of 2 closed intervals, that's a closed square. If you draw it in R2, it's this region that includes the boundary, right? So this is not homeomorphic to R2. If you look at the inside of that region, by the way, so then it is, so for example, if you look at, so if you look at a closed, okay, so this is a slightly different example, maybe. So if you look at a closed square, okay, so it's a closed square, and you look at a closed triangle. By the way, here this notion, this closed is different from the notion of closed of surface, okay? So this is closed as a set in R2, which means it includes all its limit points. So in a closed triangle, are these 2 homeomorphic? Okay, somebody said yes. Yeah, they are. And yeah, so you can do that by, let's say, one way to do that is you kind of cut it up into 2 triangles, let's say. And you can, and over here also, you can sort of cut it up into triangle. You can map this red triangle on the left to the red triangle on the right, and you can map the green triangle to the green triangle okay, by some kind of linear map. So you've already seen this linear map that, you know, sort of takes an interval to another interval of a different size. So here now you have a triangle. You can define a map that looks linear in two variables, x and y, that takes a triangle to another triangle. Okay, so you can use these maps to build a map from the closed square to a closed triangle. Let me mention another kind of example that had come up earlier. If you take a sphere and you remove a point from it, okay, so this is, so let me think of it as sphere as S2. This is what it looks like, and a point is the North Pole, okay? So then a sphere minus point is homeomorphic to R2, and this is, the reason for this is stereographic projection, okay? So you can define a map from sphere minus a point to R2 by looking at this line. So imagine that point has a light source, and then if you look at the light rays, they hit, so it will take this point on the sphere to this point on the plane, this point on the sphere, this point on the plane, and this would define a map of the sphere minus that point to the entire plane, and this is a homeomorphism. Okay, so in any case, this is what the notion of homeomorphism is. So next time we'll see a few more examples, and I'll talk about a little bit of knot theory. So that's the plan for next time.
Repeat how to. I'm going a bit back. This is
okay.
This is in the portion where you computed out the chi's. Like,
okay, the Euler characteristics. Yeah.
Yeah, over here.
Okay.
I actually tried out this example of two-hole torus kind of thing, but
right.
I was not able to. I mean, I was not able to count the chi actually. So how do you do it? Can you show it once again?
Yeah. So what you need to know is that when you glue these two guys, so let me just show them an arrow. This guy and that guy. Then the Euler characteristic adds up. Right. This is all that you need to show. Then you would know it is -1 plus -1, which is -2. Right. So why does Euler characteristic add up is the question, right? So I mean, so this you can try to do by sort of imagining the Euler characteristic counts the vertices, edges, etc., the regions, of some graphs on the two surfaces, where that graph includes a vertex like this and an edge around the boundary circle like this. Okay, and then when you identify these two, these vertices, they get identified, and these edges get identified, right? And now when you keep track of that, and then do the computation again for this glued up graph on this new bigger surface, okay, so you'll see that the Euler characteristics have added up. Okay, so yeah, so what's happening is that this edge is decreasing, and a vertex is, one edge and one vertex decreases, right? But what happens when one edge and one vertex decreases? Well, you're doing V minus E plus the number of regions, but V minus E doesn't change, right? Because you're decreasing vertex by 1 and edge by 1. So the sum of these remain the same, okay? So, yeah.
One more thing.
Yeah.
We discussed the notion of continuity.
Okay. Let me go to that. Okay. Yeah.
Give a second definition, that equivalent definition.
Right.
Yeah, this one.
Yeah.
And over here, you made a graph. This discontinuous graph.
Okay. Yeah, that's right. Yeah, this one. Mm-hmm.
Yeah. How did you get this thing that in the domain we get a closed set? I mean, semi-open.
Yeah. Well, if you look at it, what are the points that map into that green region? So in that red region, right? It's exactly the ones in the green region. Okay. So there's no other points that map to that red region. Okay.
What's not okay with me is that how do we get the closed X?
Well, because X maps inside that red region, right? So X is included in that. If you look at all the points on the domain R that map to that red region, then X definitely maps in there. And so does everything on the right, but nothing on the left, because the left one would map somewhere else, right? So it's not mapping.
Also, we
Yeah.
have some f of x's that don't correspond to any x or in the domain.
Now, when you say f of x, then there's already, you're assuming there's an x in,
I'm sorry. In the codomain.
Yeah, it could miss something. Yeah.
Yeah.
So yeah, I mean, right. So it could happen that the pre-image is an empty set. Okay. So empty sets are considered open sets. Okay. In this whole axiomatic definition. Yeah, that's right. Maybe that's a good point actually. So it's something to note is that an empty set is open. Okay. Yeah. Yeah. All right. Okay. So, I hope this was useful. I mean, you can always look up Armstrong's book or any other book also. This is just to sort of whet your appetite and sort of give you a glimpse of how some of these things are done. I think sometimes, books have to be very formal, and so it becomes, sort of a collection of definitions and so on. It's harder to process. It's always better to kind of have a session with somebody, some human, so in this case I'm the human, and so this is what this whole sort of this topology mini course is all about, right? So anyway, so thanks to StemNet, and
thank you everybody. Please don't miss the last one, and hope you're benefiting from these sessions and enjoying. And also please attempt the exercises that Professor Gupta gives you. Okay, thank you everybody. See you.